And I request yours here, Mike. Please go ahead to start the session.
Thank you, Professor Banerjee, for a nice introduction session.
Thank you, Dr. Dubey.
Yeah. Participants, now I would like to introduce our speaker for today's session. Sorry for the interruption. Dr. Ritam Banerjee is presently working as a research professor at the Department of Material Science and Energy. Although now his assignment has changed, he is now a principal engineer at Fab 1 Tech Integration Global Foundries Germany. So before that, joining Global Foundries Germany, he was actually a research professor at Department of Material Science and Engineering at Pohang University of Science and Technology, Republic of Korea. So from 2014 to 18, he was worked as an assistant professor of Institute of Microelectronics of Chinese Academy of Science, Beijing, China. From 2012 to 13, he held the position of visiting scientist at PGI 7. This is a Zurich Research Center at Germany also. Dr. Banerjee has received his PhD degree in electronics engineering from Changgung University, Taiwan in 2012. And prior to that, he has graduated from Vidyasagar University, India, with a MSc and BSc degree in physics. His keen research interests include advanced memory devices and applications. Now I request all the participants to please keep their audio in mute mode. And Professor Banerjee, now the stage is all yours. So you can share your screen as well. I request Sumit to stop sharing the screen. Thank you, Sumit.
So thanks a lot, Mayank, for this nice introduction. So share my screen. Okay, is it visible?
No, not yet. Yes, sir. It is now visible.
Okay.
Thank you.
Thanks a lot. Okay, so shall I start?
Yes, sir. Sure, sir.
Okay. Thanks a lot. At first, I would love to thank all of you organizers and also the participant to invite me for this talk. And I'm very sorry for the inconvenience because it is a second time I'm in this platform, but in the last meeting, it was the problem of my network issues. So, and many thanks to the organizers for giving me this opportunity to present my work in this platform for the second time. Well, today I'm going to discuss about the hybrid filamentary switching. Defects are tremendous possibilities. And although I'm currently I'm working with GLOBALFOUNDARIES, but this work is solely dedicated to my previous organization work. So I must acknowledge that I was in Postec as a research professor. And most of the part of this work, this presentation, you can say that it is a joint collaboration with Intel. So I just picked this topic for today's discussion. And I'm very sure that you had several excellent, brilliant sessions for different applications of materials and resistive switching devices for like neuromorphic or 2D materials. But in this case, I'm not going to give you such overview because you already have it and you guys are brilliant in that, I'm very sure. But in this case, I'm going to discuss the device engineering, and basically you can say the defect engineering and how it can actually control the switching parameters. So if you guys are very much aware of anything about the resistive switching devices, today I'm going to discuss with that resistive switching devices. And for an example, resistive switching devices, if we have like silver and copper type of structure, normally we expect that it will be like ECM type or maybe metal bridge like device. But in reality, like the oxygen vacancies, it has a huge impact to control the behavior of those devices. So today I'm going to focus in that section more. So before I go any further, I would like to acknowledge all my contributors. Definitely Professor Huang, who is the professor of this SIDP lab of Postec. and I was closely working with him and all of the students and staff members of Postec. And then I had the collaborations with Professor Chi Liu. He was from my former, actually he was my former colleague from the Institute of Microelectronics, Chinese Academy of Sciences, but currently he changes to moves to Fudan University. So I'm very thankful to him. And also for this work, or maybe for this talk, the most of the work was conducted with the collaboration of Intel and from Intel Lab, USA. The collaborators, I must say that Dr. Ilya Karpov and Dr. Ashish Agarwal, I'm very thankful to them. And some of the work related to the application of resistive switching devices for like security applications and so on. So I'm very much thankful with this collaboration with the NTU professors like Anupam Chattopadhyay and Professor Ale. So most of the work in this section I'm going to discuss, it is from those Intel collaboration and NRF. NRF is the National Research Foundation. This is from funding from Korea. Okay. So here is the outline of this talk. So at first I'd like to introduce you the emerging applications, though I'm very sure you all are aware of this one, but then I will continue this with the future scope of this research and the motivation to choose this topic, or maybe you can say that maybe further it can give you a brainstorm for further thinking process. And then I will discuss about the hybrid switches, including those both threshold switching devices and memory switches. And threshold switching is kind of a selector device. So I'll discuss both of them. And then finally, I'll conclude my talk. Okay. So let us move to the introduction section. Okay. So in our current world, definitely we are connected with a network, right? So then everything, like you can start from the industrial section, or maybe retail, healthcare, consumer, and smart infrastructure, security, surveillance, transportation, and others, many applications. It is all connected together. And most of the cases, memory is one of the vital part of these applications. Okay, let me find where I can find the pointer. Can anyone help me to get the pointer here? Mayank, can you see any pointer?
Yes, sir. You can go to this left side. Just if you can just go to left side. There are four, 5 options. The top is annotation. Annotate. There maybe you can find.
You mean this side? You can see my screen, right? Like pause, share, assign. Okay, mute participant. Okay, annotation.
Yeah, yes, sir. Yeah.
Okay, so then annotation. No, I think you can see. Can you see this?
Yes, cursor is, I think,
So,
is
yeah,
visible,
cursor is.
but you
Okay.
can do a right click and then you also convert into the laser pointer as well, I think.
Okay.
Okay, right click.
No, nothing is coming. Is something in Chinese. I have no idea.
Actually, yeah, that's difficult for us actually to translate.
Yeah, I can understand. Anyway, I'll continue with this cursor. That's fine. Okay. So I'm not very sure if you guys are aware of this chart. This is called the Gartner Hive cycle. And normally this kind of representation is for the upcoming technologies. So nowadays, definitely emerging like AI is one of the biggest approach, which is going to be there for next at least for many years, and definitely it will modify its forms, but definitely it will be there, because most of the time nowadays we are just heading towards the similarities or maybe mimicking the electronic devices with the functionalities of brain. So definitely this is one of the most hot topic you can say for the future generation. And if I give you a brief overview, it is like that. We want to mimic the similarities with the brain that the electronic device should present, or maybe at least can understand. And in this development, I must say that there is a plenty of efforts, like for several decades again, to improve the algorithms and hardware part. Now here we are already in this segment, and in this case, and you can see if it is here, like emerging devices that mimic neurons and synapses. This is one of the hot topic. Okay, even for research, at least for some next several years. So in those emerging devices, we have several options. We have several options like PCM devices. PCM is a kind of phase change memory where the switching it can happen with the changing of phase. And then we have the MRAM, and the floating gate devices are already there. And then emerging device, which is RRAM. One device is missing from here, that is the ferroelectric devices based on hafnium oxide. That also is the scope of the research for the future work. But here in this case, we are going to focus mostly on the RRAM devices. Now, for the RRAM devices, you can see the structure is rather very simple. It is just two metal layer, and then you have one oxide layer. It can be chalcogenide or whatsoever, even the 2D materials. But then if you have like a conducting path, you have the current. When the conducting path is off, you have the off state. So basically the switching based on the change of resistance itself. Now, if you have the high current, so basically resistance is low. And now when you have the low current, so resistance is high. So this is how we can define the two state. But the major problem of those RRAM devices are facing that low power operation. So here, why I said the major problem, we can achieve the low power operation, but again, stability matters. Okay. And then highly stable performance, which is the main criteria. And then we can have the high device yield. So those are the basic problems with those devices. Okay, for decades now, RRAM is in news for those emerging applications for AI or AGI and all. So RRAM, when I discuss about those RRAM devices, it is a very simple concept. Okay, now if you have let us say that silver, and this is PT, and then some kind of oxide layer. So initially you are in the very high resistance state, and then you are coming to this direction. So basically this with the biasing condition, positive bias here we are discussing about, and then the silver start to migrate, and then it nucleate somewhere on the top of the bottom electrode side, and then start to grow. And then finally it forms the filament. So basically you have the low resistance state, and then after certain voltage, if you have the negative side, so basically you will break this channel and you will come back to the high resistance state again. So now if you look at this like video diagram, you can see that there is a difference of the size of the filament, right? Now for the first figure, it looks like it is a very thick filament, sorry. Yeah, for the first one, yeah, it is a very thick filament. Okay, so now once we have a thick filament, or so basically you can understand a very stable channel form. So then this kind of devices, the low resistance state is very stable, and they can be useful for memory applications. Now, if instead of having this structure, if you have a very thin filament, okay, now what will happen? It can break depending on the field. It can break easily, and those kind of devices are suitable to use for the selector devices. Normally it says the threshold switching devices. So in this talk, I'm going to discuss both of them and how to achieve them in the same structure. Now, although the structure of the RRAM devices is very simple, okay, it's just metal layer and another metal layer in between the oxide, but here comes the main factors like how the interface can behave and how the bottom substrate it can behave. Like it can be 1T1R structure or maybe 1S1R structure, different type of structure, and then what will be there with the different annealing conditions and all. Okay, so now if I go step by step, then maybe definitely from the very top side you can change the materials thickness, different capping layers with different kind of interface layers. And then in oxide, you can have several kind of oxide layers, single layers, multiple layers, and you can use different systems like ALD, PVD, CVD, PLD, and so on. And finally, it is the point of the defect engineering, because so far I'm very sure that you have understood that RRAM is the switching process is mostly by the changing of the defects. Maybe it is oxygen vacancies, or maybe it is the metal ions. So with this defect engineering process, there are several opportunities like doping, nanocrystals, and embedded metal layers, and defective electrode designs. Okay, so in this talk, I'm going to focus for this defect engineering part. Previously, it is also reported from Leti, and and also recently from one paper is from Advanced Electronic Material. They have shown that if the oxygen vacancies are present in the standard RRAM devices like silver based or copper based, I'm talking about the ECM type devices, then there is a decrease of the operating voltage. And at some point, with the controlling of these vacancies, it is possible to have even the forming free structure. So the presence of vacancies, actually, it can dominate the switching possibility of any structure. And then another study, it shows that if we have a different kind of vacancies, and then depending on the different kind of switching material, the performance can change. So here in this work, we are mainly focusing for the silver based devices. And the issue with the silver based threshold switching devices is the highly stable performance, as I have discussed already, and then high selectivity, high speed switching, and high endurance. Okay. Whereas the issues with the memory switching devices is totally different. Some parts are same, like high stable switching, it is very much recommended. And then multi-level facility, high endurance, and high retention. So definitely we can see the major difference is the retention part, which is not really needed for the threshold switching characteristics, whereas the selectivity is one of the important part, and endurance is for the threshold switching devices. So now the major challenge is those two behaviors are extremely opposite behavior. Now you can say that South Pole and North Pole. Now how to achieve those extreme behavior in a single design? Okay, so here is the solution, that hybrid filament. Hybrid, I mean to say that where you have both oxygen vacancies and metal ions. So that kind of devices like hybrid filament devices can be one of the solution. Okay, here is a very simple device stack. It is the same stack like if you have the PT bottom, and then the hafnium oxide as the switching layer, and then you have the top electrode layer. Normally the top electrode layer is the silver. In this work, we have used the silver and copper both, but the rest of the work, it will be focused only for the silver devices, because copper devices mostly can show the memory switching behavior, but the silver devices, it has the capability to show both of the behavior. Okay, here is the physical analysis of the structure, and you can see that we have a very clean structure. This is the bottom electrode, this is the 4 nanometer of hafnium oxide, and this is the silver layer. Okay, and the density of the hafnium oxide is around 9.42 gram per centimeter cube, and the composition was like 1 is to 1.9. So it was non-stoichiometry structure. Okay, so again the major focus was the use it for threshold and memory switching, and also for the neuromorphic applications. However, that part I will not discuss today. Okay. So here is the threshold switching devices and how the initial threshold switching devices we can operate. So this is how threshold switching looks like. Okay, and the devices can be used with a different biasing scheme. Now, initially we have several biasing scheme, but I would like to focus in this case like positive, negative biasing scheme, and finally almost 80% or more than 80% devices with this scheme actually show that the devices can work really well. So what is this scheme is actually? Before the apply the positive voltage on the silver electrode side, if you apply the negative voltage, what will happen? There will be the soft filament, or rather you can say that oxygen vacancy filament, it will form inside the structure. And then you apply the positive voltage, and then it will be the silver filament in this case. So this is the vacancy filament, and then it switched to a silver filament. So normally, if we have a different kind of compositions, normally it shows that with this kind of scheme, we can very well control the initial threshold voltage, or maybe the forming voltage below 1 volt. And this is one of the crucial part, that if the forming voltage is too high, those kind of devices, it can suffer with the endurance behavior due to the over injection of those ions. Okay, now if we have different level of currents, like from 1 nanoampere to 1 microampere during the negative side forming process, the structure of the filament, it will change. It will totally change. When you have a 1 nanometer, or even say that low compliance devices, then the structure is mostly like threshold switching type behavior. But when it goes for the high compliances, definitely you can understand the oxygen vacancies will be much more higher. So then when you apply the positive side, then there's a much better injection of the silver. So it can give a very stable filament, but again, it can go for the very low resistance state, and the device can switch to the memory switching side. So those are the dilemmas of the same device, but with the proper biasing scheme, we can change it. Now here, with the proper biasing scheme, we can see the selectivity we can achieve like 10 to the power 9. Okay, and with the sub threshold swing around 1 millivolt per decade, and which is quite good. And for the selectivity is at least 10 to the power 9, something like that. Okay, so the steep slope with high selectivity, it can achieve with the negative small reset process, but again, it is achievable. Previously, there are many groups, they have tried to design those kind of devices with silver, mostly with the silver devices. You can see the famous groups from University of Notre Dame, Suman Datta group, or even Professor Wang's group from Postec, and also others. The major problem was the variation of the threshold voltage, and definitely you can understand the variation of the threshold voltage, it is not good at all for any kind of devices, this VT shift or VT variation. So the major concern was that how to control these devices. The DFT calculation in this case, it shows that when we have the silver ions very close to the oxygen vacancies, then it has, like, you can see the close proximity like 2 angstrom or something like that, then it has the binding energy almost like 1.5. Okay, now when the silver ion is actually further from those oxygen vacancies, the binding energy is very low, and again with the presence of those vacancies, it can attract the silver ion, and the formation energy of those kind of filament, I'm talking about this filament, is very low. And this is exactly the DFT calculation. It shows that the behavior is exactly as proposed by C. Latti and others. So in this case, what we did, we achieved this kind of behavior with very highly stable threshold switching and all by design the structure of the filament. Initially, we have this vacancy filament, and then we place the silver in a very close proximity of the vacancy. So in that process, we basically localize the filament in the structure. Okay, and that is the reason of the improvement. Okay, now if we have if we change the compliance from like 10 nano ampere to 100 nanoampere, then definitely the threshold voltage will be shifted. Again, this is due to the over injection of the silver into the vacancies. Now, as compared to the normal scheme without any vacancies, now when we have the vacancies, definitely the distribution is much better. But the major improvement, it was there when you see the uh, the off conductance change for the without vacancy and with vacancy structure. For without vacancy structure, it easily can fail in the low resistance state. So here, what do I mean by that fail low resistance state? Normally the high resistance state, it can stuck to the low resistance state, and there is the failure of the device. And for those devices with the hybrid filament, it was very stable. Okay. However, the stability was also to some extent. So here, the further work was done with the alloy electrode, which is silver tellurium, and also some other alloy electrode was there. So with the silver tellurium alloy electrode, you can see in this case, if we have the fair comparison of silver with the silver tellurium, so normally for the silver devices, there is always a possibility to increase the conductance towards the higher side. So it means that the filament actually can grow over the switching process. But with this scheme, the silver tellurium is actually showing very stable and very close to like 1G0 conductance level. So the failure probability of those silver devices is always stuck to on state, and the failure probability of silver tellurium is always stuck to off state with this kind of scheme. Now, to understand those behaviors, if you can go for the simple nucleation behavior, definitely you can see that in this structure, if we consider this is the radius of the filament, so now after a critical radius, the memory switching behavior can happen, and below the critical radius, basically the nucleation process is very limited, so the full filament growth is not possible, and this region is suitable for threshold switching behavior. So after the theoretical calculations, we have seen that the barrier height for silver devices and as compared to the silver tellurium devices, and also with and without those NPN scheme, it shows that with the vacancies, it can increase the barrier height, and also the same goes true for the silver tellurium devices. So the main origin of this behavior comes from the difficult nucleation in those devices. So here is the model of the filament, how it can looks like, and better you can understand from the schematic image. So initially with the NBLC scheme, we form the vacancy path, and then with the positive scheme, we form the silver path. So basically this filament is actually a combination of both. So after the rupture process, you can see the complete filament, it will not definitely break, it will break in some part, and that is how with a very small voltage, a very stable switching we can achieve, because we do not have many diffusions of silver in random locations. We have a very localized diffusion. So then it is the endurance measurement. We have checked the endurance. Without this kind of special scheme, the device can show endurance up to like 10 to the power 3 or something like that. But with this special scheme and with silver tellurium devices, we can achieve the endurance like 10 to the power 9 cycles. Okay. Now, when it comes to the endurance, be careful, because actually this endurance data was taken from many cycles. So here it is the plot of the decade, like 10 to the power 1, 10 to the power 2, something like that. But when you will measure, you have to check different many cycles, almost all cycles you must check, and you check that how it is going on. And then you must do one thing, you must do the yield check. Only one device, single device endurance is not enough at all. So you just check random devices and maybe several devices, and then you get the endurance probability. So in this case, the silver tellurium devices, it cannot work for 10 to the power 9 cycles for all the devices, but at least more than 60% of the devices, it can work for 100 million, like 10 to the power 8 cycles. Okay. So here is the summary of this threshold switching devices, and you can see that different groups work is presented here. And normally with this scheme, which we have obtained here, like hybrid filament formation, with this approach, we can actually minimize the variation of the threshold voltage less than 3%, and with the very high selectivity of 10 to the power 9, and definitely with very high endurance of 10 to the power 9. So now the next part is that we can obtain this kind of behavior with a limited compliance. When the behavior is uh, almost like 100 microampere in that level. But when it exceeds the limit, like more than 100 microampere, definitely there is a widening of the filament. And that is the reason the switching is no more the volatile switching. The volatile goes to the non-volatile switching. Okay, because you have a thicker filament. So now, if you see in this simulation, this work was done by DL Mini Group, Professor Mini Group, and it was published in Nature Communication. So now, if you see here, if you have a thick filament, please concentrate in the time. So yes, you can see the time to break the filament, the simulated image. When you have a thick filament, it looks like almost like 0.1 second, or it can be even larger. It depends on the thickness of the filament. Now, if you have a thin filament, thin junction, okay, so it's just 0.9 millisecond, or it can be even lower. Again, it depends on the thickness. So basically, when you have, so you can say this is the major difference between the threshold switching and memory switching. So threshold switching, it can define with this kind of structure, and memory switching, it can define with this kind of structure. It's very clear. And now, if you have a different kind of compliance label with the same scheme, so previously, if you remember that I discussed for the threshold switching, the scheme was like nanoampere range, but now you are in the microampere range. So when you are in the microampere range, you introduce the more number of vacancies into the channel. So basically, now your filament is much stable. Okay, and so now you need certain amount of voltage to reset the filament. And this is how we can change the switching process from the threshold to memory switching. And here you see the same structure, same silver, hafnium oxide, and platinum structure. It can show a nice memory switching behavior without changing any material. Okay, and in those devices, even we can achieve the multiple labels with just proper tuning of the compliance current. Now here we must understand one thing, that when you do the scanning of this reset part, you can see several jump of the labels. Okay, now in terms of quantum conductance, though I am not claiming that this is quantum conductance, because you must check it in the like 4K, or in suppose in that temperature. But again, to just rough estimate this one, that how the transition is going on, you can check this kind of structure like CV, and you can zoom in on the structure, and you can see there are several jumps. Okay, so you do not have only jumps like 6G0, 3G0, 2G0, some, or like not only the even or odd jumps, but or maybe the integer jumps. Rather, you have some half integer jumps like 1.5 G0, 0.5 G0, 4.5 G0. Those are really obvious. Now, if normally in the ECM devices, if you have a very pure metallic filament, okay, so you know the conductance of the metal, it can change as the integer value. As you can see in this figure, it like from this is a nice scanning, like from 10 G0 to 1 G0 level. Okay, so basically if you go through this side scan, you can see that like 1, 2, 3, 4, like exactly like 10 steps are there. However, those kind of data is very difficult to achieve, but it is possible to get those kind of references for pure metallic filament. But once you have this kind of mixed filament, or maybe any impact of those oxygen vacancies, you can have multiple intermediate steps. So in this case, when we operate the devices with like 10 nanoampere range, so you can see we have a very clear scanning like 6, 5, 4, something like that. But then when we increase the preforming current level, then basically the half integer values actually start to increase. And then when we have like 10 more than microampere range, it is like full of mixed integer values. So basically it can change the complete switching process of the devices with the presence of the vacancies. So now we can say that even the structure is the same, like silver, hafnium oxide, and platinum, but it is no more the ECM type of devices. It is rather a vacancy and metal filament. So this is the full range of working devices. Now, with this behavior, you can change the threshold switching to a complete non-volatile memory switching in the same stack. So this is how you can play with the defects inside any kind of materials. Previously, from Sematech, it was reported that if you have the high current level, you can see in this figure. This is from Sematech, and if you have the high current level, your number of defects, it will change. Like in this picture, you see when you are in the range of B, it can represent the number of defect 2. When you are in the range of D, it can represent the number of defect maybe 8 or something like that. So you can understand if your channel has more defects, so the current will flow more. So this is how when we use higher current, so we introduce more defects, and then the switching transform from threshold to memory switching. And here is a nice example and how you can see this, visualize those kind of filaments. This is by the scalpel AFM image, and you can see this is the hafnium oxide 5 nanometer hafnium oxide stack, and this is copper blue layer, and how this is it can form the filament. Yes, so this is how the filament it can form, and this is a TM image. This is the copper, and this is from some other work, but it is good to visualize the filament. Yeah, concentrate in this region. Yes, sorry. So this is how the filament can form and the actual switching process can take place. Okay, so now come back to our topic. So we have two different kind of process. One with the low compliance forming preforming process, one is the high compliance preforming process. So in both process, you can see one filament is very fragile, but other one is very stable. It is just due to the over migration of the silver into the channel. And the device itself is very stable for the memory switching behavior. You can see this is the consecutive DC switching cycles for 10,000, and it was very stable. But the LRS was ohmic. It was pure ohmic, and which was quite expected because of the silver migration. But the HRS, it was like semiconducting behavior. And again, the statistical behavior, it shows that the device, it can work like device to device variation. It was well, but again, please remember this statistical distribution actually can define like a certain amount of devices is like 25 to 30 devices, but it is not on the full wafer. So you can understand when it goes for the full wafer, this distribution, it may increase. So that is one of the biggest problem with the RRAM devices is facing right now. And here is the endurance and retention behavior of the devices. This is the endurance behavior. You see the same device which can show the threshold switching with like 10 to the power 9 switching cycles or 10 to the power 8, something like that. The same device, it can show the very good memory switching with 10 to the power 8 or even more. And it has a nice retention behavior. Now, if we compare this with the other reported work, it shows that the silver devices with this kind of scheme, it can continue for 70 degrees centigrade at 10 years. So far, why I choose this silver, it is very difficult to get the excellent retention because silver, normally the diffusivity is high. So whenever your channel is there, it is easily, it can break easily. So that is the reason we choose this topic, and to increase the endurance behavior of the silver-based devices. Previously, the similar kind of design with the silicon dioxide, it was proposed by Toshiba, yeah, in 2019. Okay, so here is the overall summary of the memory behavior and how it looks like. You can see the all silver-based devices with the different kind of switching matrix. But in this case, we have a very stable memory switching behavior, and definitely it is the very much tunable resistance state. It is based on the preforming condition, and so far we have achieved the best endurance and retention behavior for the silver-based devices, and we have highly controllable multi-level switching behavior for silver-based devices. Okay, so let me conclude this talk. And in this case, we use the silver hafnium oxide platinum structure, and we use the same structure to achieve both the threshold switching behavior and also the memory switching behavior. Now, by proper tuning of those vacancy path, we can achieve excellent threshold switching behavior with like high endurance and selectivity. And at the same time, with the proper tuning of those structure of the filament, we can achieve excellent memory switching behavior with high memory window retention and endurance. And for any further read, you can follow those papers. Actually, mostly this advanced functional material and IDM are closely related to that. So thank you very much for your attention, and you are open for question.
Thank you, sir. Participants, if you want to directly ask some of your questions, now the floor is open.
Yeah, please go ahead.
Hello.
Yes.
Yes, Professor Banerjee, greetings of the day.
Thanks a lot.
It was such a nice talk. Nice talk. Actually, I am working on this resistive switching devices.
Oh, great to know that.
Yes, I am working on these perovskite oxide thin film based devices,
Okay.
barium titanate and lanthanum orthoferrite and other perovskite oxide.
Okay.
Yes, sir. My first question is how we can quantify the effect of this oxygen vacancy and silver ions in the filament formation.
Yeah, this is a very good question actually. The point is that we didn't perform that kind of experiment in this case because already there are plenty of reports available for TDDB, and this is the time dependent dielectric breakdown. And in this case, the good part, or maybe you can say the easily understandable part of resistive switching devices, it is that it is a soft breakdown process which can conduct the filament. Okay, so now there are plenty of references are available which shows that if you have like if you goes through those gate dielectric I mean the conventional oxide devices, you can see that if we have depending on the current level and voltage level, if we have the higher voltage, it can create more defects in the oxide. Okay, and normally those for any kind of non-stoichiometric devices, you can have a large amount of oxygen vacancies inside the stack. So now when you have the depending on those external parameters, these vacancies can align, and depending on the current level, you can have the thicker or thinner channel. That is how the gate dielectric can damage. Okay, so now in this case, we use the similar concept to basically break the film with the soft process, or maybe you can say the soft breakdown process. It is not soft, it is actually ultra soft. So we don't want to break the film completely. We want to just tune the film, or maybe channel the some amount of oxygen vacancies. I'm not very sure that how many vacancies or something is there, but definitely it is confirmed that when you have the low current like 1 nanoampere, definitely the oxygen number of oxygen vacancy is much lesser as compared to when you have the current level like more than 1 microampere, right? So then the thickness of the channel is also much lower as compared to that. So we this was based on that assumption. I do not have the pure quantification of those values, but definitely the work was conducted with that approach because our main objective was to get the localization of the silver path.
Okay, sir. And second question is now actually I have done earlier, I have published a work on this barium titanate. Write once, read many kind of resistive switching. Hello?
Okay, yes, please go ahead.
And sir, in this sequence, now I have started to insert a layer of silver in between the two successive barium titanate layer.
So, okay, basically silver nano layer or maybe nano, okay,
Yes.
okay.
So after doing this silver nano layer in sandwich in between this barium two barium titanate layers, now I am getting resistive bipolar resistive switching.
Yes, you will get, yeah.
But this the on-off ratio is very low,
Yes, it will be.
and but sir, in both cases, I have taken the top contact from silver itself.
I didn't get it. Can you, what is your top electrode?
My top electrode is silver and bottom electrode is FTO.
Okay, I got it. So what is your question?
Actually, earlier I was getting WRM kind of characteristic. It was
Yes.
forming one time, and further when we are
Yeah, basically
applying the voltage,
it stuck to the low resistance state. So
yes,
let
yes,
me guess, your forming voltage was more than 1 milliampere.
forming voltage was
Sorry,
1.5.
forming current was more than 1 milliampere.
Yes, no, no, sir.
How much?
It was like, it was more than 1 milliampere.
Yeah, it should be. It should be 1
Yes,
milliampere, because when it is 1 milliampere, then only you have a very thick filament, right? If I'm not very sure that what is your mechanism, but if it is even the filament, so you can understand more than 1 milliampere current means you need a very thick wire to form that. So now once it is formed, it is very difficult to erase that. You cannot break it,
yes,
isn't it?
yes,
So that is the reason whenever you store there, you are always there. But in this case, in the second case, when you have the so if you are okay with that, let me try to understand your stack first a little bit.
yes, sir.
So, okay,
My
so
first bottom electrode is FTO coated glass substrate.
yeah. No,
Then
I'm
barium.
clear. I am clear. So whatever I'm telling you, let me know I am true or false or correct or
Yes,
wrong. So
yes,
from my point of view, what I can see your device, actually it is silver, the first this one time forming filament. It is like you have the 1 milliampere current or even more, like 10 milliampere, something like that, in between maybe 5 milliampere. But again, it is more than 1 milliampere. So in that case, you have a very thick filament. It's like a stable filament, which is very difficult to break. So that is the reason you can form one time. It is difficult for you to get back the your actual high resistance state again. And
yes,
then if you check the initial high resistance state, I mean before forming, you can see
yes, sir.
that when you have the silver in between, silver middle layer, or you say, what is the thickness of the middle layer? Is it something like 1 nanometer, 2 nanometer?
Yes, sir. 1 nanometer.
1 nanometer, yeah, that is what I expected. So now when you have a 1 nanometer layer, it cannot be a complete layer. It can be like nanocrystal. I'm not say nanocrystal, but nanoparticles. Like, so it
Yeah,
is kind of
it will be
doped.
like nanoparticles.
Yeah, so it will be like doped structure. So now when
Yes,
you have the doped structure, so automatically your initial resistance, the virgin resistance of the device, it will be high. So if you check that one, you can see the device without silver nanoparticles or nanostructure or doped structure, the device with silver dope structure, the initial resistance, it will be high.
yes, sir.
Am I correct?
Yes, sir,
Okay,
definitely.
so and I guess your resistance, it will be sorry, your initial current, it will be somewhere close to 100 nanoamp or something like that, or it can
Yes,
be.
sir. It is like 100 nanoampere.
Yeah, exactly. It should be like that. And then what will happen? You automatically cut down your the high resistance part. So
Yes,
you are already in some middle layer. Okay.
yes, sir.
In between that range. So when you do the scanning, when you go for this, now what will happen? You already have the silver in the stack. So now your
Yes,
top silver is actually not moving that much. It is the
yes,
silver present in the stack. They are playing the part to create the channel or maybe the
yes.
switching path
With the oxygen vacancies,
with the
because
oxygen happen. Yeah.
my layer is amorphous and I don't provide oxygen flow during the process.
Okay. Okay, yeah,
So
so I have understood. So that is the reason. Basically, you have a very thin filament, right?
yes,
So now what will happen? It will be much easier to break it.
okay.
And I am sure that now your current is like lower than 1 milliampere.
Yes, yes, sir.
Yeah, it should be. So then you can break it. So there is no problem. So whatever you are doing, it is perfect. It is the right thing.
So,
If
sir, my question is like this: earlier I have proposed the role of oxygen vacancy, the permanent formation of filament due to high thickness of layer,
yeah, due to high thickness of
but
which layer?
the barium titanate layer,
Yeah,
it
that
was,
that
yeah,
part.
it is 200 nanometer thick.
Okay. Yeah, that is okay. But honestly, if you are definitely if you have high thickness, there is the high probability of more ion diffusion because you have to overcome those large gap. So definitely
Yes, sir.
yeah, that is okay. So what is your problem now?
Sir, actually, I am struggling to propose the what kind of filament theory I have to propose for this study. Actually, I am getting stable resistive switching
Okay.
with the moderate I on-off ratio in compared to earlier study.
Okay. Yeah,
But
that that
we don't have that much facility, so we can do TEM with this
no, I can
for this filament.
I can understand your now if you want to explain this as I mean from my point of view, as I can see your structure, it is very straightforward explanation that previously it was a very less amount of defect because silver was not there. It was not silver doped structure. It was simple silver, your stack, simple, finish. So now in that case, your top silver layer, it has to overcome a 200 nanometer gap, right?
Yes.
So you apply the voltage and your voltage, it takes like 1.5 volt to diffuse there. And when it diffuse there, your, sorry, what was your initial forming voltage?
Sir, initially it was forming at 1.39 volt.
That's okay. So almost 1.5 roughly if you check the
Yes.
device to device. Okay.
Yes, sir.
So then it can form, silver is very, very easily diffusive material. So it can form a very thick filament. Okay.
Yes.
Now, when you have those silver doped structure, now your top silver, it has it has nothing to do to diffuse for 200 nanometer structure
Yes.
because it is already doped. Now,
Yes, sir.
when you apply the bias in that structure, what will happen? Those silver, it will start to migrate and whatever, I'm not very sure that how much oxygen vacancies or whatever structure you have. But anyway, if the silver is there, there is the high probability that you will have a silver filament. Okay.
Yes.
So the silver will start to migrate, and when you apply the positive, so what will happen? The silver will start to diffuse towards the bottom side, FTO side. Okay. So now your bottom is FTO, right?
Yes, sir.
Yeah. So now it will deposit on the FTO and it will start to grow the chain. So now you can understand your actual bottom electrode is not the real electrode. So in this case, your bottom electrode become a virtual electrode because with this additional growing silver from the bottom. So when you have this 200 nanometer thick layer without silver, it will reduce to some extent.
Yes.
Okay. And you know, the major advantage when you have a conical shape like whatever bottom electrode, definitely the field will be very high on the top of that, right? Apart from when you have a plane surface, the field on the plane surface is much lower as compared to the if you have something on top.
Yeah.
So now your most of the concentrated electric field will be on that virtual electrode. So that is how you have a very thin filament. And as you have a thin filament, now you have this bipolar switching behavior because if it is a thin filament, you can break it easily.
Yes.
Okay. So whatever you propose in your earlier work, that it is
Yes.
a big filament and So that is true. It is already there because it was undoped structure.
Yes, sir.
So here is a clear, straightforward explanation because this is doped structure and this is how the silver can migrate and it can deposit on the surface of the bottom electrode and it can create the virtual electrode. Now you have the high electric field on those virtual electrode. So basically it can localize your field and also you can get your lower performance or maybe the bipolar switch, whatever you want to explain.
Yes, yes.
Is it clear?
Yes, sir. Thank you. Thank you for wonderful discussion and you explained me all the things thoroughly. I am very grateful to you. Thank you, sir.
Most welcome. Yep.
Yes, thank you, sir. Participants, anyone else want to discuss any queries related? Sure, sure.
Sorry, I cannot hear your voice. Hello, Mr. Raj. Yeah. So, sure.
Working on displacement current based resistive switching memory devices.
Cannot hear you properly. Can you please repeat?
I'm working on basement current based memory devices.
Okay.
My doubt is just like this, sir. How can we check the selectivity of this material, sir?
For the selectivity of the material, you just check how the transition of the voltage is. Okay. So you just check how the device is switching from the off to on. Okay. So let me say one thing. If your off is 10 and if your on is 100, okay,
Sir.
so your selectivity is 10. Hello, can you hear me?
Yes, sir. Yes, sir. Yes,
Yeah.
sir.
So it is just you check the current, that what is the switching of the current from how low to how much high. So this is your selectivity.
Just like simple resistive switch on off ratio, sir.
Yeah, exactly. It is simple resistive switching on off ratio is just the different terminology because this device used as a selector. So it's very clear. So when you say the selectivity, we can understand that okay, you are discussing about the selector.
Sir, it's based on PA sir, in which intermediate layer is based on bismuth ferrite. But here I have one doubt again. How can I check the selectivity of this all these three? Yes, sir.
Okay. So if it is is it a threshold switching device?
No, sir.
Okay. So you check where is your off current. What is your off current?
It's around 3 amperes, sir. That is sir. Because
Sorry, your voice is not clear to me. Maybe Mayank, can you hear it clearly?
No, actually, Shazia, even I cannot hear you. You can type your question in the chat box as well. I will ask on your behalf. So, sir, Dhananjay is asking another question. This is
Sure,
in
please
the
go ahead.
chat box.
Okay.
He's asking what can be the reason for the threshold switching intermingling with the bipolar switching?
Okay. The problem with the threshold switching is threshold switching and bipolar is bipolar. But the thing is that in this case, the major difference is for the threshold switching devices, or better to say that for the selector devices, the major difference is the structure of the filament. It is either threshold switching or memory switching whatsoever. The major difference is the structure of the filament and how we can form the filament. So now normally in any resistive switching devices, although most of the time switching occurs in one position, because once you have the filament, the rest of the filament stop. So basically you have one filament, but there are many small bridges it can form inside the oxide layer. So when you have those threshold switching behavior, you already have a very small, thin, tiny bridge. That is true. But then when you are continuously repeating the switching cycle process, so continuously you are doing this back and forth motion of your ions, of your mobile ions. So what will happen when you have this kind of behavior? there is always high possibility to diffuse more ions in the channel. It may not be from the top electrode, but definitely you do not forget that you already have some amount of deposited ions inside the oxide stack. So when you during the switching process, it also can play a part, and it can widening the channel. So once you have this wider channel, then it is very difficult to turn it off. And in this case, you need to apply a minus voltage, negative voltage, which actually the reason for the bipolar switching to break the channel. So it is only how we design the channel. So that is the major concept of resistive switching. You say resistive switching, memory switching, or threshold switching. All are in the same roof, resistive switching, but that major difference is how we design the channel. That's it. Yeah.
Thank you, sir. Anyone else in the participant want to discuss anything?
Hello, am I audible?
Yes.
Oh. Hello. Yes, thank you for the talk, Professor. Just one more question along with the previous one question. I'm Dhananjay here. So
Hello,
my
Dhananjay.
question was, my question is, when we are doing this threshold switching, there is a spontaneous dissolution of filament is happening, right?
Yeah.
So, but sometimes what happens is that it doesn't happen, and we
it will stuck to on state.
Yeah. So is there this kind of phenomena is very general in case of
It's very
threshold
normal.
switching and resistor switching, or like over the period of cycle when we are repeating a number of cycles, so we get this kind of behavior for everything and this is normal, or this comes into the faulty category of the devices?
Yeah, thanks a lot for your question. But actually, definitely this is a faulty category, but this is normal behavior. And here comes the major challenges that how to overcome this one, right? So if you carefully look at this part, let me go back. Yes, so, okay, if you look at this part, you see, I use the silver, right? So
Yes.
the over the switching period, you see the growth of silver in terms of conductance, it was in the higher side. Okay, so now if this is like 1G0, just for reference, you see it start from 2G0 and it's landed to like 6 or 7G0, right? So basically there is the growth of the filament, and this is true for all the threshold switching devices. So that is the reason the endurance is very limited, and you can easily have this kind of bit error rates. It is very high, and this is not beneficial for those devices, and that is the problem, that why RRAM devices cannot, it still in the research, why people are struggling. So this is not a good behavior at all. Yeah, so you must have to overcome this kind of behavior. This is not at all good, and there you need a brainstorming for to how to overcome this process.
So as of now, do we have any kind of already like a standard of procedures set up for this kind of problems?
Yeah, that is the reason I show you here. Instead of applying this one, I use the silver tellurium, right? This is my IDM paper.
Okay.
And you
so
can go
you
through
are
it.
just changing the top electrode. Sorry to interrupt, but just changing the top electrode means that you are trying to control the ions, like Ag ions, to be imparted into the active electrode layer, right?
Yeah, exactly. Because what will happen? We have the AGTE, right? So now
Yeah.
AG is not free at all.
Yes.
So someone is there to hold AG back. So now what will happen? The diffusion of AG, it will be very limited. We do not
But
need.
it will result into the increase in the voltage for like switching, which
Yeah,
will
it will
eventually increase the means like it will defy the low power what we are trying to achieve.
No, not at all. You can see here. Yeah, this is true. It will increase the voltage. You see, for this is with the AG. Okay, let me increase. Yeah, this is with the AG. This is with the AGTE, and the voltage difference for the AG is just 0.3 volt. For AGTE is just 0.6 volt. So it is anyway. It is lower than 1 volt. So your voltage margin is perfect. No problem.
Okay. And one more question is, Professor, when
Yeah.
you were showing the linear like line of something, there was one slide. If you go
Okay.
back, if you could please go back on linear of point something where you have shown that, yeah, this one.
Yeah.
So is this kind of something like within, if your device is showing the switching within the 100 microampere current compliance range, so it will always be counted as a volatile threshold switching?
No, not at all. Volatile will counted when it can easily come back to high resistance state. Even if you are working with the 50 microampere and then your device is stuck to the low resistance state, it is not volatile. Volatile means when it forgets the low resistance state, right? It
Professor,
can
I'm
be
trying
even
to
10
say just
microampere.
reverse thing. Like for example, I am able to get the non-volatile resistive switching states,
Okay.
but within this less than 100 microampere range, like for example, 50 microampere or 20 microampere. So
Okay.
will it be counted as a non-volatile memory switching, or it will be counted as a volatile threshold switching?
No, definitely it
Memory.
depends. Like, yeah, no. This is perfect. So if you have like 50 microampere, definitely it will count if it has retention.
Yeah.
Remember, if it has retention, it even for like 50, like not the microampere, maybe less than 1 microampere range. Okay, if you have retention, then definitely it is non-volatile type.
Okay. Thank you very much, Professor.
Yeah, welcome.
Thank you, sir. Sir, only a last question. This
Yeah,
is in
sure.
the chat box.
Yeah, sure.
Dr. Harinder is asking, sir, what sort of simulation tools we can normally we can use? Like if the persons are not having fab facilities or something, then what sort of simulation tool would you like to recommend?
Well, I am not a simulation guy, but definitely I will. Actually, for the simulation, there are many simulation tools are available, but yeah, maybe the maybe I think the if possible, Monte Carlo is good, and anyway, there are many possible options are there. But anyway, Monte Carlo will be good one. Yeah.
Okay, so thank you.
And then you can also use in a console as well if you are doing.
Yeah, exactly. Yeah, exactly. Console you can use, but it is a very beginning.
Yes, yes.
Yeah, exactly. You can start it. Yeah. I think there was also a question from Sazia. I think we miss her.
So she has not still responded to the chat
Okay.
box or anything. I think
Okay.
Shazia, if your voice is now okay,
I
your
think
audio quality is okay.
she is not online.
No, she's
Sir,
not
if
here.
time permits, I do have a question, sir.
Yeah, sure. Please go ahead. May I know who is this?
Good afternoon, Professor. That was a very wonderful talk. Thank you for that, sir.
Is it
In
Anurag?
your yes, sir.
Hello, Anurag. Yeah.
Sir, in your presentation, you were talking about localization of filament.
Yeah.
Was it the physical position of the filament you were talking about, or it was something else, sir?
Exactly. Physical position of the filament.
So how are we going to control the physical position of the filament, sir? Like when we apply a voltage, the diffusion of Ag ion, it can start from anywhere from the contact. So
Exactly.
how?
You are right. You can visualize this very easily. Like uh, normally when we have a simple structure, we do not have any barrier. It is like falling silver from the sky. It is like raining of silver, right? We do not have any place to protect them. Okay. So now you can think something like that. You have an ocean. Okay. Now you want the water of the ocean to come exactly in your agricultural area. What you will do? You will cut a channel and bring the ocean inside. Okay. So in that case, your ocean water will not fall down anywhere. That is exactly what we are doing here. We are preparing the channel for the silver. Definitely, I am not claiming that silver will not diffuse some other places. It can. Definitely it can. But it will be very minimum because you already have the localized channel with those oxygen vacancies, because it is a very soft breakdown path is already created, right? So that is the channel for the silver. Silver will flow through this channel. So you can think as a ocean what is coming to your ground.
Okay. That means when we are fabricating the device, at that time itself, you are creating a channel in the insulating layer. Like in some
Yeah,
paper,
that is
stress
the main.
induced etching was there. They have
Yeah,
introduced
that is the main engineering part, that how you can do it. That is the main key.
Okay, Professor. Thank you.
Welcome.
Yeah.
Thank you. Thank
Ma-
you,
Mayank,
Professor
Mayank.
Banerjee.
Mayank, can I ask one question
Yeah,
to
yeah, sure,
Professor
sure,
Banerjee?
sure.
Sure.
Yeah,
Go ahead.
yeah. Dr. Banerjee, actually, I'm also doing on the work on the Memristor devices, basically based on the Y203 based Memristor system.
Sorry,
But
which one?
Y203, yeah, yttrium oxide.
Okay, yttrium oxide. Okay.
Yes. So basically, my question is related to the industry point of view, because of recently, I think Webit Nano, the industry are working on the silicon dioxide based RRAM devices, and then fabricated in a 4 MB, I think RRAM to launch that. So basically, what is your point of view to industry to shift the another oxide material like hafnium and Y203 and something else other in comparison to the SiO2?
Actually, both of like I was working with those Intel projects from quite some time. Okay, so it is not only the silicon dioxide that it is in the industry.
Okay.
Like if I can give you example for TSMC, they are working with the hafnium oxide. Intel, they are working with the tantalum pentoxide. So it is not the silicon dioxide only material, but all of those industries, they have their own selections, they have their own process lines and everything. They have their own process materials. So most of the time, the focus of the industry, it should be the one material which they have, and they know the reliability is excellent. They want to go with that material. Okay, so it is not only silicon dioxide. Yeah.
Thank you.
Welcome.
Yeah, please.
So feel free to ask me if there is any more. Yeah.
I think sir, now there is no question. So, sir, thank you, Professor Banerjee, for such a wonderful and a very entertaining talk on hybrid filamentary switching. So, and sir, we are very grateful for the time and effort you took to share your experiences with our community in IIT Indore. So, thank you, sir. We will definitely like to interact with you once again. Probably we'll plan in next year also. So, thank you very much.
Sure.
The wonderful talk, sir.
And thanks a lot for inviting me in this wonderful platform. And I'm very happy that you guys have a lot of questions. It is always better to have the interactive session rather than
Yes,
just
sir.
a talk. Yeah, it is.
Yes, sir. Exactly. Definitely.
Yeah. Anyway, thank you, and I wish you all the best for your happy weekend. Okay. And
Thank you,
with
Professor.
research, and apart from the research, take rest. Okay.
Yeah,
Sure,
thank you,
sir.
Professor Banerjee.
Thank you.
Have a good day.
Thank you, sir.
Yep. Bye.
Have a nice day. Have a nice day, sir. Thank you.
Yeah. Thank you.
Thank you, everyone.